Oh, yeah.
I mean, who's the?
Whatever, the major domo.
I would say,
Oh, no, I just said shoot because I would never say shoot. I'm trying to be nice. Trying to play the game. Everybody like how I dressed up? My dress apparel. Yeah, I was not. I'm like, man, I should go buy a shirt. I was gonna go buy a shirt real quick, like run to TJ Maxx, but I'm like,
That's not good.
that's you.
yeah, so you have something on.
I'm off.
Because we had it before and Ken shut off.
I got nothing. What do you say? It's there somewhere. Okay.
Which one is the pointer, Jim, for the button?
Let me see. Turn on that button there
Oh, okay.
is the thing, and it shows up, and then you can go forward and back with the other thing plugged in.
Yeah. Oh, this top one is the laser.
The top one is the laser, and the other two are going to work forward and back. I didn't feel like sitting sideways, so I can touch. You feel free and you.
Movable. Movable feast, right?
Right time to upset your cup.
It is actually
That's
12:59.
Then no,
I could go over here.
I couldn't get the thing to just.
Wait, more people, I don't care.
Well, yes, we will.
There's 22 people.
Plenty.
Thanks. I found those families that are on, Bert on the seas, Al, Barley, Chris Potter, Dave Davis, Potter,
Ooh, Chris Potter. I haven't seen Chris in a long time.
James Ford, Jim White, Julia, Chris Young, Caitlin Frizell, Mark.
JN,
Yeah.
hit the swap display button.
What do you want me
You're
to do?
projecting in the wrong.
What am I doing?
It's displaying right up there, but it's
What
not.
am I doing? Duplicate slideshow?
Hit the spot.
Swap presenter viewer?
He's got to be able to mirror the screens, though.
Yeah.
You know how to mirror the screens?
Mirror the screens? What do you mean?
Okay, I did this in class the other day.
Oh, I don't want this shit up.
Right, well, you have to mirror screens on your settings for video.
All right,
Might take high-tech tech support from that.
That's my nap.
mirror screens. I don't see this.
Go to settings.
Where's settings?
It's on your computer.
Yeah, I'm in this.
No, you got to go into your computer settings.
Yeah, I can't get to them from this.
Stop projecting for now.
Stop share.
Stop share. Go into your computer like you normally would.
How do I get over there? Oh, I'm over here. All right. Yeah, man, it's not letting me get.
You had to get to, on your computer where you have settings where you do things to your
Yeah.
computer.
Do you see the image that's on my? Oh, all right, there you go. Here, it's down here.
Okay. There you go.
I know I look like a computer
Notice the
tough
fun.
guy, but I don't know. Where am I?
Let me see. I can't see with my glasses. System gaming.
What are you trying to do?
Mirror
Display?
display.
So you want to be on the other one? Go back out. There was a display.
It was?
Yeah, to the left. Right at the bottom, right?
Where?
Yeah, right, you were just on it. Oh, system. See, it has display in it. It's under system.
Okay. Rearrange your displays. See what it says this?
Yeah.
And now it's got to be set to mirror. No,
Scroll down.
Don't see the mirror.
Go down farther. Go all the way to the
Yeah,
bottom.
why don't you?
Don't only need text one display.
I don't get it.
Oh, wait. Right here.
Yeah.
This right here?
Yeah.
Extend,
Duplicate the thing.
second screen only, duplicate, right? That's what I was just in, duplicate. That's what I'm in.
Do second screen on. Now go in back into and share.
You don't want the sidebar.
It's got to project it.
This right here, right?
Yeah, no.
Don't you just click
Click
that?
that button.
Oh.
And when you're done.
No, not that one.
That worked.
Yeah, we don't want subtitles. Though.
That's good. We're now mirrored both on the screen and online.
He's not broadcasting. He's not gonna be- So if he shows uses the laser pointer, they're gonna see where they're gonna sit.
Am I still up
They're
there?
not going to see it.
Well, that's what he wanted to do. That's why-
Yeah, well, I want to be on there. Yeah,
He wanted to have the camera show.
yeah I want a camera showing.
He was gonna- he was gonna-
The camera showing in the upper right. They're not going to be able to see that.
Yeah, that's, well, I want, we're recording this, right?
Yes. But the recording is just going to show that little screen in the upper right hand. I think we should just move on and get started.
We'll be able to see the screen in mine, right? Like they'll be able to see it through there.
But what you wanted to do is be able to point to something and have the audience see it.
Yeah, I mean, you know,
All right,
I
back up
can't
the
get it.
slide and let's get started. That's as good as you're going to do.
I'm fine, as long as I can see this, as long as I can stand up, you know what I mean, this is also for me.
This is fun.
And then it records me so I can do what I want.
Yep.
Takes a minute. Is my audio coming over?
Can everybody hear JN? Can
Yeah.
everybody hear JN?
Yeah, we can hear him.
Yes.
Good, thank you.
Well, say something, Diane, so they can
Yeah,
hear you.
just wait for this to, there you go.
All right. Let me unmute for 1 second.
Actually,
To avoid feedback, I will step up here and simply introduce JN. So JN Stanley is here to present the results of his master's thesis. JN has received undergraduate degrees in anthropology and then in geology.
History, geology.
history.
Poli-sci.
But for the past about 7 years, he's been working in the core repository, and he decided he wanted to work on a master's thesis, and he was taking classes. And we had JN working on various projects already on strontium isotopes and helping out with cores. But JN had volunteered to go into the Maya jungles and help archaeologists, and discovered an old tool sitting in the core repository, ground penetrating radar. And he held it down for fun to see if it would help out in the investigations in Belize. And I want to give props to Carl Swisher, who recognized this and said, well, that's a very old GPR. The department should chip in and buy a new GPR. So JN got a new toy, and he took it to Belize the following field season. And he came back and I said, JN, just write up what you've done from the Maya work for your master's thesis. But he also then continued to apply this more locally to Sandy Hook. And so his thesis actually has two themes, one which is Maya and one which is Sandy Hook. Without further ado, JN.
Woo, long overdue, 2-year degree, 5 years. COVID, thank you. All right, so evaluating effectiveness of near surface geophysics to interpret different geological environments. So the goals for this research were to apply ground penetrating radar and use multi-channel analysis of surface waves, MASW, both remote sensing techniques in 2 completely different geological settings. One is in northwestern Belize, which is part of the Corazal Basin and attached to the Yucatan Plateau. So it is a Jurassic Paleocene Cherney limestone. Sandy Hook is a siliclastic quartz homogeneous beach. So in Belize, we use GPR and MASW to look for subsurface features that the PI was hoping existed. They would have been related to already excavated and already mapped in structures of drainage basin systems that ran down the Rio Bravo escarpment and a ball court area that we were looking for a drainage system. At North Beach and Sandy Hook, we used GPR to look at 2D imagery of progradation, facies models, and basically just overall beach morphology. And we want to see if we could, dissect this over time from dune to swash, a 350-meter transect. This is the Three Rivers region of Belize. In red over here, Chawak Bateau, that is our site. If I don't know if you can see it, but it sits right on the Rio Bravo escarpment. The Booth River and the Rio Azul, they make up the Three Rivers region. The Rio Azul is in Guatemala. They both feed into the Rio Hondo, which goes out into the Caribbean. The Rio Bravo and the Booth River both, the Rio Bravo and the New River, which you can't see, both sit on escarpments. And there's a third, which is in Guatemala. This is considered the Maya lowlands. And the area that we're actually researching is the late classic period, which is around 700 CE or AD. It wasn't there, maybe 200 years it was occupied before we would kind of lose track of it. Sandy Hook. My image to the left is Rutgers University highlighted in red, sitting right on the Raritan. It runs about 30 miles out to Sandy Hook. It drains into the Raritan Bay, which is connected to the Sandy Hook Bay and the Lower Bay, which is all actually part of the Hudson Estuarine system. It is the lower segment of it. The middle is actually Sandy Hook, an aerial photo. The caption at the top, not the Sandy Hook one, but the actual colors. The key is the shoreline changes from 1835, 1932, 84, and 2000. Really, basically, only really got to look at the purple, which is 1835. And if you look at 2000, there's a lot of changes. It is heavily eroding in the south. It is growing in the north. And this is 20 years ago, and North Beach has grown, I think, about 200, 250 meters since in the last 20 years. It's expanding pretty fast. To the right, the image, that is just the little square at the top. And the inset is, this is North Beach. This is our transect area from dune to swash, 350 meters. And by the way, I just want to note that this map in the middle was done by John Smeltz. So quick basics on ground penetrating radar. So ground penetrating radar works off electromagnetic waves. It is very similar to acoustic, sound waves, and how it penetrates velocity. How velocities work. When you have a change in density, you get higher speeds. So ground penetrating radar works the same way, except instead of changes in velocity, we use changes of dielectrics. So every material has a dielectric. Some are more conductive than others, air being the least, water being the most. Air sits at 80, I can't even see that.
One.
All right, air sits at 1 and water sits at 80. All right, I might ask.
He can't.
Yeah, I can't see. It's all right. It's all right. All right. So air is at 1, water is at 80, and basically the changes in between them and how each material within that medium sits will give you, a reflection. When the reflection is really high, and you have these really high amplitude reflections, like you see over in this GPR profile, these really dark black and white ones, they're really high resolution because that means there's probably a drastic change within the dielectric itself. When they are really close to each other, you get these more medium amplitude reflections. And then when you don't see anything, if it's there, but it's not staticky, it's just very low amplitude reflection. You can kind of see in the middle how it works from this signal oscillating behavior. It's just a change in dielectric, how it goes from negative to positive. When it's right in the middle, that's your very low. When it's completely extreme on the left and the right, these are where you get your really high, high amplitude reflections. And then the bar on the middle on the right-hand side, that just shows you where we were: dry sand, wet sand in Sandy Hook, and then limestone, dry and wet in Belize. So in GPR, we use, like I said, electromagnetic waves, specifically microwaves. I can't see the frequency. It sits within 1 millimeter to 30 meters. What is it? 1 millimeter to 1 meter.
That's what the slides.
Okay, yeah. So 1 millimeter to 1 meter. I'm sorry, there's something blocking my view of these. The side. They are shorter than radio waves. You can see my little microwave on the side with the cheese. All right. MASW works off sound waves. Any Transformers fans, you see sound wave in this little bottom area right here. Sound waves are specifically longitudinal waves. They work off of an active source, so specifically a 16-pound sledgehammer from my research, and they are surface waves. Specifically surface waves, they are Raleigh waves. They travel near the surface of solids, they're longitudinal, and I have a misspelling there, but they are transverse motions, AKA ground roll. Ground roll, if you know anything about earthquakes, is usually the most damaging area because it moves in 2 directions as it rolls across the ground. This is what our stuff looks like in the field. These are our little toys, our accessories. The orange box is like a 1x1 by, I think, 6. You have obviously a handle so we can pull it. The wheel on the back is like it's a distance wheel. It's a survey wheel. It replaces time. So, time is constant, never changing. But when you're in the field, it's not realistic. You have to stop. You have to back up. You have things that where when you run in time, you can never go back. You're always in time. So you lose a lot. And it's just a lot more work. And it's a hassle, especially when you're in the environment that we are in when we're in the rainforest. You have a fiber optic cable. This one we have is since outdated. We've got a much shorter, much better one. And then the pretty little blue box up against the tree, that is our SIR 4000. It is the control unit, and it is the basis of everything that we get our data from. And then to the left, these 2 images are just examples of the kind of images that we saw in Belize in this karstic system. We're hitting bedrock really low, and that was pretty consistent all throughout Belize. All right, so this is our MASW stuff. We only use this in Belize. It is a lot of equipment. We carry this out into the field once. We leave it in trunks. We wrap it in tarps, keep it dry because there's 60, 70 pounds of gear in plastic containers that we have to walk in and out if we were to do it. We usually just bring the battery back to keep it charged, the laptop that's hooked up to it. But we have 16 geophones. We have our cable that the geophones hook up on. This is an Ethernet cable that hooks up to the machine, to the computer. We have another cable that hooks up to the sledgehammer with a switch that lets us know when recording starts. It's a lot of stuff, too much to carry in and out. So like I said, we leave it in the field because we're in the middle of a reserve, so no one's out there anyway, so it's safe. This is at the top of the screen to the right. This is just an example of the kind of images that I get with the MASW in Belize. This is Sandy Hook. These are all our toys in Sandy Hook. The 400, the 100, and the MASW. The MASW at the start, top left. We were out in the field. I don't know if you could, oh shit, sorry. I don't know if you can see it, but there's a couple holes in the ground. There was a lot of snow, a lot of ice. It doesn't look like much until you try to drive a hammer through it with an aluminum metal plate. And we got nothing. And then COVID happened shortly after this. So we really never got to go out there and try to collect data with this again, which kind of stinks. Maybe in the future we could do it again. But we did get great GPR data. The bottom is the 400. It's in a 3-wheeled cart. The 3-wheeled cart, we don't have the survey wheel hooked up to it because there's one built into the cart. There's a blue cable that runs our fiber optic cable into the control unit, which is at the top. Top right is the 100. It's a monster. We have a survey wheel hooked up to it because it does not fit in the cart. And so we couldn't use that survey wheel. We got a little creative, tied a rope to it. This way we could mount the control unit on the top and basically just push it. It wasn't easy because the sand gets real deep. Lucky every time I did the 100, John was with me. And we did this one together. The 400 you can run by yourself, but the 100 you definitely need. All right, so site 1, the drainage basins. The PI, Dr. Stan Walling. He was interested in to see if there was a continuation of these drainage basins that he has already found in outcrops. He has mapped in. All the walls that he has found are symmetrical. So that means that the Maya were very specific on angles, very specific in the direction things went because everything was based off of the stars. So north, south, east, west, it's very specific. So he wanted to see if there was a continuation. Were they artificial? Were they natural bedrock? Or did the Maya come in, which they're known to do, and they take bedrock that's already there, they carve it out, they manipulate it, so they don't have to do any heavy hauling. The limestone's really malleable, so they can do whatever they want with it. This is the drainage basins. This map on my particular view is a little distorted. Hopefully you see it a little better. But this green image right here is on a map. It was published. It was done maybe like 5-6 years ago. It shows the top unit. It says basin H1. That is the main basin on the top of this little plateaued area right here. This image right here that says labeled H12, I believe that it's said and thought and pretty much known within their archaeology community that a structure sat on top of this. And then the BWs are the basin walls, which reach out. All this was outcropped. So when they broke it up, when they started excavating, they kind of already knew for a fact that it was there. It ended up being a complete structure inside. So, it's believed that this particular structure would fill up with water and then it just runs down the escarpment. Each one of these basins probably collected water for water management, soil management, both, one or the other. But it was definitely used for some kind of catch basin. All right, so moving on. This is a profile down the transect up to 68 meters or something like that. I can't see.
You can use my screen.
Oh, cool, awesome. All right, yeah, so it's about 70, 80 meters. Yeah, it's less than 80 meters. So if you see the map up top, the red lines, the yellow lines, they coincide with the profile below it. The red lines labeled 1, 2, 3, 4 are the red line number 1, the yellow line number 2, then 3, then 4 is down the transect, which ended up being a feature unknown. 1 was a wall that it was mapped in, it's outcropped, it's tied in, it's symmetrical to the wall that you just saw. Yellow was in line with this. It gave us a similar look as number 1. Number 2 gave us a similar look as number 1, but there is no outcrop here. There is, however, a very large tree root that sits over top of this. So this could be from the root itself, or next field season, they may excavate this and see if there's anything underneath this. Now, number 3, which is also outcropped up at the top and tied in and mapped as an existing wall and part of the second part of basin 3, the outside wall of basin 3, we don't get a good signature of it, but it's been tied in, they know it exists. So, it leaves questions on whether or not, how much of this is actually a multiple, how far does it go down before we see it, or is the material within that same close range of a dielectric where it doesn't continue to give off a signature. As we go down, once we got out of this mapped in area, we took the transect all the way down to the end, just above north sign on the the compass. This wall right here, we did not know existed, but as you go down this this is terraced off. So you hit these flat spots, flat spots, flat spots. This sat within a flat spot. We got this signature labeled number 4, which is at about 43 meters. And it was very interesting to the archaeologists. We also got this image over here at 50 meters, but 4 was kind of the concentration. So we excavated 4. There was 3 days left in the field. The PI was like, I want this done. So they did a 1 by 1.5, which you can see in 4A and 4B is exactly the same image, just from different angles. So the black and white arrow points north. So you can see they're going, one is taken from the south, the other is taken from the east. But that is what it looked like. This is bedrock, limestone. Like I said, it's a little churty. And we tied this in as a possible wall. It gave a lot of signs. They need to do further excavation. But like I said, we had 3 days to do all that. It takes a lot longer than you think to actually excavate the unit and keep it, right. So this is what this looks like. Sorry. Number 4, this is this. That's what it looks like from an actual real life angle. All right, so then we did the MASW along the same transect. We did a 20-meter transect. We ended up doing it after the excavation itself. We had problems with the equipment out there, just various pitfalls that we had. But we ended up taking it after. I didn't get to look at this data until I got back to the States. But if you look at the top image, you look at the bottom image, they're obviously not the same. They're different distances. So I tied it in what 8 meters is on each. 8 meters coincides with the basin wall up top. And then this labeled number 4. This is the basin wall that we excavated. This is the same image. They run over exactly the same spot. Now, this image that I said was actually pretty interesting. Turns out that there's another high velocity in this particular corner exactly where it is, which led us to believe that this could be an addition to the basin down the escarpment. This being before it, these are really low velocity S waves. This could be organic matter mixing with broken up carbonates, and and it's slowly, as you get with depth, it becomes a little more cohesive. So the MASW turned out to really accommodate the ground penetrating radar, like a really good tool in hindsight. It would have been great if we could have got this in the field, but it was at the end of the season that we got to really actually do some of this stuff. So so this is a further project for next time we go out. All right, so the ball court alley. The ball court alley had one specific goal, and it was, is there a pitch from the north end to the south end? Water was really important to the Maya. They had the water god Chak, and everything was, dedicated to him. So water coming through the ball court would mean that it's ritualistic, and it allows it's more of a sacrifice to the god as they allow rain to come through. So it's a good possibility that could have been manipulated, but we weren't sure unless you excavated the entire ball court. So we did GPR. The map to the left is just a larger map of the one you saw before of the basins. It is this circle right here. This is the ball court mapped in the larger. This is just a small section of a very large map of the entire area of Chawak. This is the map that I made along with the PI, Dr. Walling. The orange dashed lines, that is a 7-meter transect that we ran from wall to wall. It's different. There's a lot of this is falling down. So, it's like 6.7, 7.1, but the gist of it, the average it's 7 meters. So each one of these is a cross section of the ball court itself. This white dotted line actually goes off an excavation, G, C, D, A, and E and F. These are all excavated. The X's, SCB and SCA, are both ground samples that I took with a hand auger, a one-piece hand auger. Just wanted to see how far we went down before we hit something solid. This right here was at 28 centimeters. And this one down here, SCA, was at 32 centimeters. It's a gradual change. It may have meant nothing, but when we look at our results, it could be tied into something larger. Okay, so the 20 lines that we did, the east to west transects that we did. And I think it's important to know that you see this flat, all these profiles with the MASW and the GPR, but the machines and the equipment does not take in for topography. So it's always going to look flat, even if it's a little off. So the graph I made over here, it is depth from surface to time slices north to south. So there's 20 time slices here. They start, the first two are 0.4 meters or 40 centimeters. They vary up, but you can see you hit a high point here at 0.45, 0.5, 0.55, and then here at 0.56. So you have this nice trend of these higher, elevations, if I may call them. And there is, without a doubt, from north to south, over 20 meters, a 0.6 degree change in gradient. You don't need much for water to roll. So this confirmed what the PI had thought, and this was a successful, experiment with the GPR, and it was nice. We backed that up. We also did the MASW on here. Same map of the actual structure itself, but we have one transect line that runs 38 meters. On the graph to your right, it's 40 meters, but that's because the software rounds it out. The dashed line is where we had our geophones. We only had 16 geophones. So if you do the math, we have to leapfrog every 8. So we continually get this movement with the geophones. So you can make up for the fact that you don't have a lot of geophones, which was successful. To the right, you have the cross sections. This is an S-wave velocity cross section. Again, the red, the light, the violet, that is lower 40, 70 and up, lower S-wave velocities. And you get into the highers, which are the yellows, the greens, the blues. So still, it's about the same depth as on the basins. This image up here that I have in a black circle, if you look up here, it's probably hard to see it on the larger screen, but it's green. This is exactly where, on the map to the side, that coincides with this, all these excavated areas. The fact that it's just on the top and it starts to get down, this is all excavated and it's backfilled in. So the material is probably not as cohesive and random, but it's still close to the top. We have these little basin-like structures like we did on the other one, but you can see they get smaller from the north to the south, kind of showing or indicating that there is a change from this top surface to the bedrock as it goes down. The depths are questionable, to be honest, but they do coincide with what we're finding when in comparison with the GPR. We do have these dips though from the erosional patterns that we saw on right here in the time slices. We have these deeper dips. They're not that much, but once it starts, this karstic limestone starts to erode, it fractures pretty easy below it, and it will continue on. As you go down the slope, if you look on the map to the right, these blue circles are actually a wall. And then between that wall is a little path, and then that runs and loops right down into the escarpment. So it's kind of like they set it up this way just to kind of swoosh down and run down the escarpment into the floodplain, into the river. This is what this is all about, water flow at Chawak Plateau. It's important. This area, Group H, is very ritualistic. Sinkholes, there's caves that they've excavated, sweat house, a sweat lodge. There's no really living quarters in this area that they have found, or nothing has indicated that it is. But you can see right here, when you look down at the basins, water flows down into this arroyo. And then up top, this is flat, this plateau. And then it kind of, the water reaches around here. This goes into a terraced area, which is off map. And then it also flows through the middle of the ball court and meets in with the basin down the escarpment, which leads to the arroyo. Anyway, this is what it's all about. There was a lot of confirmation with the stuff that we did. So it was pretty successful, this particular 2019 field. So Sandy Hook is a completely different animal, super interesting. It's important. Sandy Hook is just a huge sink for sea level change and data to be collected on what's going on at one of the busiest embayments in, the world, all the shipping receiving going into Manhattan and the Passaic and, Newark and Elizabeth and everything like that. So there's a lot going on here, and there's a lot of just anthropogenic anomalies and effects that are being pushed into this area. So can we run the GPR and the MASW and various areas of interest to see if we can collect any kind of data that will show us beach morphology, the process in which it has prograded out from the dunes to the swash? Why is it moving so fast? Is there lulls within that time? Is it decadal, millennial? How good is remote sensing and these applications that we could use down the road? And can we use, LiDAR? Can we use other things? John was a huge contributor in all my research because we use a lot of RTK, and we have a huge cross-section topo map that you'll see. Sorry, it's not a map. It is a topographical cross-section, and you'll see it. But this is, John did a lot of research on this. So we were really able to tie in the topography with the subsurface stuff. And also just keep in mind that everything looks flat, but when you look at the inset, you'll have a topographical cross-section. You'll see how it completely changes, and it actually affects what we're looking at. So this is North Beach right here, our transect 350 meters from the dune to the swash. On the right-hand map, these triangles facing towards the sea, purposely, each is a section that I did on the GPR. The GPR only allows me 36 meters to look at per section. So these are in 36-meter increments, but because I'm so smart, I tied them together. And we get this one long continuous 68-meter, and the rest of these are all like this. I kind of just overlaid them. They fit nice for the most part. But all right, so look, so the top, this is what I look at in the raw. Definitely know that the red and the blues are added. It's usually just grayscale. And the grayscale is actually really good, but this particular image these colors that I added, it's very small. It's only like, some of these just completely change everything. But I use these just so you can really see the high amplitude reflections. And that's what these colors are. They only show the highest of amplitude reflections. So what I did was when I broke this down, and by the way, the top image is in time. It's in nanoseconds. The bottom image is in meters. I had to keep it. It's small on your screen, but the bottom of the 400, all the 400 ones, the bottom of the nanoseconds time scale is 54 nanoseconds, and the bottom of the meters is 2.75, all for the 400. So when I broke it down, I actually broke this down into 3 sections. I used this first high amplitude reflection layer that is at 1 meter down here, the blue line. And then this other blue line was the next highest continuous high amplitude reflection, and I used that and I tied them in together. So I broke this down into 1, 2, and 3. That does not necessarily mean that it's stratigraphy, but it is how I was able to kind of sit and look at it. So in 1, we see these top layers, these oranges. These oranges represent progradation dunewards. It's only at about 20 centimeters. Sometimes you get down to about 50 centimeters, but it's high enough close to the top of the surface that the wind this probably changes. If I did this same transect every day, it would probably be a little different every day. After a storm, it would probably be completely different. So the yellows are progradating seaward. They are a lot more distinct. This dominates from the dune. And right here at 0, this is actually, I think we're like a meter on top of the dune. So we're already in it. So these yellow lines are the prograding duneward. This first top blue line at 1 meter, identified as a water table. I did that because these prograding yellow lines completely go right through it. There's no break, there's no stop, there's no unconformity. And then this second blue one, they appear to do the same exact thing. So what I'm thinking is that this is a lens, a possible freshwater lens that is just sitting on top of an already saturated lower area. Down here, this 3A, 3B, and this labeled rip-ups because they were originally all different profiles that I stitched together. You can see these really chaotic high amplitude reflections. We're calling these rip ups, as far as like they are storm induced. They're very chaotic. They're super random. But they all throughout this entire transect that I'll show you in this 400, you will see them all in between like 1.5 and 2 meters, and they are consistently through the entire transect. This is the topographic cross section. This right here is A and half of B. You can see in this cross section that we are starting to go down into this super low, which is only 1 meter above this blue dotted line down here, which is at 0, which is mean sea level. So we really hit this low because right now we're up here just before this breakdown. So what we're going to see in this next one is going to be the other half of B and C. So this is a little truncated. It picks up. But what we're looking at right here is that continuous, you see the blue lens, what I'm calling a lens, comes into this one. Number 1 starts to go to the rise, which is down here, which we start to get into this low. And then this pinches out. Then this is heavily prograding a lot. You have these ripped ups, like I said, these continue on until we get into this really big low in C, which also coincides with this huge trough. I mean, when I say huge, I mean, this is at 88 meters. This is at 116 meters. This is long. And this is almost 10 feet deep. So this is huge. It's a huge feature within this growing shore phase process. We also have this, what I identify as a foul wag. It's this little V point, which suggests that there's a lot of high energy, fluids, ocean, seawater, ripping through here, flying up north from a North Shore drift. And then you see these back and forths. You see the rip ups, of course, but you see this trough, this bar. You see another trough, you see another bar, trough. And it's a back and forth as it's prograding seaward, it's prograding duneward, and there's a lot of activity going on. This is, all right, so this is the end of the transect. This is D. We skipped everything in the middle because it's just, it looks exactly like this, but without any end. So same thing, we lose our three levels. We lose that after that pinch out of the lens. This blue line represents what I believe to be the water table. We see this top layer of these duneward prograding surfaces, the beach one, the seaward prograding surfaces, more lengthy, they're building outward. The dune ones are just, probably, it's probably tidally influenced. So you have the prograding packages, and then again, rip ups. And this is consistent throughout the entire thing. Once we hit the complete saturated zone of the swash, this is the break area. I think the front tire of the cart actually was getting hit by waves, so we kind of had to back out quick, but we get complete attenuation. Over here, we get a little something you can kind of follow. This out here, which I kind of mapped down here, but it's faint, the signal's really low, and then once you get here, it's completely dead in the water. So this is where we lose everything. This is D. You could also see this berm right here, which is about here. It's actually about here. And you can see how there's like kind of a rise and fall here. So there's like, this is the berm or about here. Like I said, there's a lot going on. It's just hard. You don't get it as much because of, we can't adjust for topography, although there is a feature within our software that I'm trying to learn a little bit more about. All right, same transect, same line, dune swash, the 100, Sandy Hook, New Jersey. All right, so this is our only really good line. This is A to B. This goes from 0 to 64, 65 meters. This area at the top that you cannot see, it's all heavy, high amplitude reflections, is because the 100 is a lower energy, so it has longer waves. So we lose that high resolution near the surface, but we get these amazing progradational features that are at 20 meters of depth at this bottom right here, 130 nanoseconds. So you get these huge prograding surfaces. You can just see them. Sorry. excited. All right. Yeah, so you see this prograding surface, then you kind of see this out, it goes into a channel, and then there's more growth over top of it. And then at this base level, at number 4, what I call number 4, because I broke it down the same way, 1 being what we have nothing on, 2 is where we start to get a little bit of prograding surfaces, 3 is just super active, and then 4 is where we just see this really flat shore face. There's not a whole lot going on, whereas, you know, how long was that there? How old was that? And then we have these, you know, these prograding surfaces going over top of it. All right, so this is with the 400. Like I said, you don't really see with the topographic map. You can really tie in the 400 with it, but the 100, not so much. It's hard to say if you know how much this actually ties into it. This is really the only area with the 100 that we got any data. The time of year that me and John collected this, there was still a lot of activity on the beach. I feel like it was maybe September or the end of August. It was COVID, so there wasn't a lot of people out, but there was enough people out where, you know, there was a lot of walking on these lows. So they were saturated because it's August, it's raining all the time. And then you just got people, you got park rangers driving over it, quads, trucks, all that stuff. So that did not help. So basically, the whole purpose of this was so we could see what kind of, if we could make a Thesis model of Sandy Hook, this transect at North Beach, this 350-meter transect. So this being the most absolute interesting of our 400 megahertz antenna, where we have the longshore troughs, the bars, we have this really big prograding surface over here at the left, around 88, 90 meters in distance, and then we have the Thalweg. This is the kind of stuff that we can see with the 400 megahertz antenna. And I believe that we can actually probably get a little deeper with the 400, playing with some stuff. I've learned some stuff, and there's a lot of stuff, things, if you tweak certain controls and how many scans per minute we do and how many scans per seconds we do, we could probably actually make this a little bit deeper, which we're going to try in the future. But with this, we see this steepening dip, you know, the rip ups are huge. You also see this hyperbola, which is related to the sandbar, you know, because of the signal coming out of the transmitter is a cone shape, you get the hyperbola. So this is exaggerated on, you know, probably how long it is. Yeah, this is the kind of Thesis models that we can map with the GPR. This is a textbook Thesis model. It looks exactly like what we have. Here's your beach, your trough, your sandbar, or your off bar. It could also be called a runnel. Your changes in high tide, low tide, which actually is probably what changes the change with that lens, and then not a lens. And honestly, if I probably ran that same transect right now, that lens probably wouldn't even be there. Or it might not be there. The tides definitely are constantly affecting the saturation levels of the water. The season is, you know, depending on how many people are using the beach, this all ties into what we get. So knowing exactly what time of season you're going and tracking what's going on at the beach is actually pretty important. So we did the 100 and the 400, or may I say the 400 and the 100. So we could kind of fill this gap with the 100 that we knew we weren't going to get. So we get 50 nanoseconds of time with the 400, which approximately ties into about here, just before all these high amplitude reflections start to, you know, dissipate. But you can see that they're kind of timing in. And like I think I said before, if we were to change the exaggeration on this, you could probably tie this one heavy one into one of these right here. So the purpose for this is called nesting. It's where we fill a gap and we tie the two together to make up for lost signal. We also have a 300 megahertz antenna, which at some point I'd like to run out here, and maybe we get a little bit more resolution for any kind of in between of this little rough spot right here. So the shorter waves, higher frequencies, higher resolution, this ties everything in together. So the one big thing that we definitely come across, the major problem with this is attenuation. Once we hit a saturated area, we no longer get any signal. This was done with the 400. This was done with the 100, 20 meters in depth. We can't even get past, you know, the area that has the high amplitude reflections. The 100 is definitely problematic in the sense that we've gotten way less recovery along the one transect that we've been following this one transect. We've gone out there multiple times. We've had to redo them because of issues we've had or complications. But with the 100, we got mostly attenuation along that 350 transect. We got 68 meters of really good data. And then we get a couple breaks down the transect, which I didn't add in because it was just a little too much. But you get these little breaks where it's on some of the highs where you get a little bit of, you can see a little bit of reflections, but it's nothing that you could really tie into anything. So in conclusion, where are we now? We still, we haven't really had a chance to go out and get more data, but we would like to go out and get more data, myself, John, Ken, Jim, everybody, and make a 3D model. I can put together a really nice 3D model with the GPR and the software. It's very time consuming out in the field, but once you get a finished product, it actually comes out really good, and you can break down layers and levels of strata. And we'd like to explore with that. Where are we going with this? So actually, we'd like to continue from the most erosion areas in the south, run a bunch of transects all the way up to the very tip at the north, maybe some on the base side, and follow these once or twice a month and see what kind of changes we get, and kind of see actually measure changes. Is it real heavy? What does it look like after storms? No storm for a while. Everything that kind of would affect changes of erosion and growth. I think that's about it. Acknowledgments. I did this for fun. I did this at 5 o'clock in the morning. So you know what? I want to thank me. This was hard, man. I started out with one. I started on another project that got canceled. I did a year of that project. It got canceled. Ken suggested I jump on this because I had all this data. So I did. In 2019, we collected our data, and then we've been out of it up until recently. So staying motivated to finish this when I was just tired of looking at the same friggin' data all the time was very overwhelming sometimes. And I know it is for everybody because we all talk. Got to thank my mom, because she's always been my biggest fan. My family, my friends, my committee. Ken for giving me a job. Jim for keeping me in line. Greg for doing the same. Dr. Stan Walling, Chrissy Taylor. They helped me. Chrissy was like my partner in the field, Stan's project. And then John for helping me do everything in Sandy Hook. My friend Emily, who lives out in Canada, I was stuck out there for a few months. She kind of kept me motivated while I was out there. GSSI, Peter Leach, has been my absolute teacher for this, and I've been a pain in his ass a lot. And then I just want to thank all the bars and bartenders and liquor stores for keeping it going during COVID when times got tough. Other than with that, I'm done. Thank you. Long was that?
40 minutes. I invite you to unmute and ask.
You want to unplug this? Oh, no, I guess I can.
Yeah, I guess.
No. Here, we good?
Well, no, we can use this. I invite you to unmute and ask questions, or I'll just put them in chat and I'll read them. You convinced him, Jay.
Nice. I'm okay with that. Could talk about this at the bar. Yeah, nothing.
I hope it was clear to everybody.
I have a question for Jan.
Barry.
Go ahead, Barry.
Well, congratulations, Jan. That's a great talk, and
Thank you.
you did a lot. So that's great. Well, my question is that, so are we able to create like a 3D volume with that tool or no?
Yeah, so I've done so in Belize. It's it looks good. there's a little bit more to it than just doing the 3D, but we were doing, I've done a 3D section and we just overlapped the antenna every 20 centimeters, so really high resolution. It's just completely overcutting itself, but the imagery was great. It's just, I think the 2D helps so you can actually have an idea of what you're looking at first, maybe run it in a couple different areas. And then kind of, so this way you can kind of decide how big you want your grid to be. I mean, you can do it as big as you want. As far as I know, I don't think there's a limit on the actual software, which, if it ever got that big, but I know we've done some pretty, I did actually that ball court I did in a 3D image. We did everything north to south. It came out really good. It wasn't what we were looking for. So the data is just sitting in cyberspace somewhere, accumulating dust. But yeah, the 3D imagery is something that we've talked about doing, and we'd like to do it, wherever. I know you work with faults and stuff like that. A lot of people use them for faulting systems. So yeah, there's applications for it.
Sounds great. Thank you, Jan. Congrats.
There's some very nice comments I'll point JN to. Congratulations from Carl and Melissa and Chris Potter. Bravo, JN. That defense seems like a PhD defense. Talk to your committee. I had to read that.
There you go. I'll take it.
That's from Melissa.
5 years, that works.
Yeah, 5 years. That's good.
I got enough credits.
I will remind everybody, as a part-time student, the target for a full-time master's is 2 to 2.5 years. So for a part-time student, and in a couple COVID mulligans, it's not untoward.
Yeah, well, I'm open to it.
All right, if there's no other questions, let's unmute and just give JN another hand.
Thank you, everybody.